Yeah, welcome to the last session of this Unit 2. In this, we are going to discuss about linear two-class classification. In that one, logistic regression and cross-entropy cost, logistic regression and softmax cost. In between, what exactly the major differences we may discuss. Okay, so before entering to this, let us discuss how to open the hyperlink as we discussed in earlier session. uh, Even here also you can see that exercise, yeah, conclusion, right? Yeah, so that's the link which is given. Go to this link. Okay, give me a second. Okay, so that's the link. Copy this link and go to browser. Open this. So the website will be opened like this. Okay, for your reference, uh, the website will be opened like this. And these are the chapter PDF, exercises, notes, presentations, the textbook. Even you can download the textbook freely here, chapter wise, and even PPTs also you can download. And yeah, exercises, wrappers, and data sets. So these were the data sets. X for exercise problems, related data sets are available chapter wise. For example, we are in the chapter 5. In chapter 5, you may see that in the exercise will be in Google Colab. So you can open in Google Colab and you can do that one. I think that we have shown in earlier, but anyhow, we'll see here. You can see that one by one. What is a 5.1 to 5.1, 5.2, 5.3, 5.6, 5.7, 5.9, 5.11? So in this one, you can, for example, here, textbook, okay, fitting a regression line to the student depth data. So here it is asked that fitting a linear model to the US student load depth dataset shown in figure 1.8. Figure 1.8 means in first chapter. Okay, this is in the first chapter. Raise a student load. That's what I asked you to every individual. Please go through the first chapter also to understand what exactly the machine learning is. So here a question asked related to this. The question is fitting a regression line to the student depth data. Fit a linear model to the US student load depth dataset shown in figure 1.8 by minimizing the associated linear regression. By minimizing the associated linear regression's least square problem using single Newton step. It is also known as normal equations. That normal equations. Okay, the normal equations. Let me show you again. Yeah. So these are the normal equations. How you are getting the normal equations is already explained. So in this way, we find the normal equations. In this way, we find the normal equation. How these normal equations we already explained, because here with respect to A and with respect to B, here we were asked to compute a straight line. We were asked to compute a straight line. In that one, x value and y value will be given to us. Now we need to compute only A and B. So to compute A and B, I need to find the single Newton. That means stationary points I need to compute. At a stationary point, gradient would be 0. That exactly I'm using here. So First, I computed the cost function, and the cost function. Okay, let me erase this. Eraser. Right. Okay. This is the cost function. At the cost function gradient is equal to 0 with respect to the here unknowns are a and b. That's what it is asked here. Okay. So also known as normal equation. Those normal equations are nothing but this is sigma y equals to na plus b sigma x, sigma xy equal to a sigma x plus b sigma x square. These are known as normal equations. No normal equations. If the trend continues, what will be the student debt in 2030? In 2030, if it is the same, it is following means it's extrapolation. It is asking. So in that one, let us fitting a regression line to the student data. In the student debt data. So how the student debt data it is opened. Okay, where is this? Right. Exercises, presentations, PDF, downloading wrappers, data sets. Which can be downloaded, maybe exercise required data sets. So data sets can be downloaded from here. ML refine data sets. In that, accept all. Supervised learning data set. We are in the supervised learning data set. In that student data set. Yeah, this is a student debit data set. If you open this would be that. X value and Y value it is given. X value, Y value it is given. And this is okay. So for this data we are supposed to compute this. So if I show you that in this data set, MLR refined data sets, we are in the super learning data set. Student data set. This is the student learning data set. So how many actually it is given in the two rows. One is X value, another one is Y value. Up to this, totally there are 40 students. In textbook we checked only for 5, but here it is given 40 students data sets, 40 X values and 40 Y values. That is what. So like this. Now that student data set is student debit data set.csv. We are asked to load that. So for the loading the data set, np dot. So for that one, what exactly we are doing is import autograd. Autograd means gradient and wrapped numpy. Autograd wrapped numpy. That we are importing that package. For that one, here we are using import autograd.numpy as np. This entire is as an np. So this is np is an alias name. And data path to data. So here we are giving the data path in the website mlr find mlr ml refined. This is ml refined, that is a textbook name. In that one data sets, in that one we are in the supervised learning data sets. This is the path. From that path it is fetching the data. So in that path it is choosing this data set, data path plus this is the data data set name. So yeah, by default here my data path would be in the link data path would be given this. There is an error. The error reason is here it won't accept the data path because the data path is not available. For that reason, what I'm checking is I'm using data path is from my local machine. At my local machine D, generally we are writing the file location would be like this. So my file location, okay, this is the file. In that, go to this information. In the information, copy path. So if I copy the path, it would be look like this. Here, where if I pasted here the path, if I pasted here path, it is showing some error. What is the error? Let us explain this. Actually, the error would be escape sequence is missing. Escape sequence. Instead of this slash, this is a backslash. Now I need to use forward slash. Then only it will be working. Otherwise, it won't work. Now it will work. See that here. So there is no error. Now you need to change the entire path here because it is checking the path. It is checking the path. So that path you need to paste here. So like this here you need to identify the path. In this path we are importing the data set. So here the path already we are given data path. To the data path, this particular data set that I used here. So this at this here data is npload.txt. This is a txt form, load.txt csv name. The csv name is this data file will be uploaded in that. Delimiter is comma separated variable. That's the reason it is .csv. And here x 0 comma colon comma 0 colon means from starting to ending. Extract here 1. So extract output for this data set. These are the total student data. Now print np shape and print np shape y. Shape x shape y means how many number of elements are there in x and how many number of elements are there in y. That is we are expecting here. So this is 40 and 40 are available. That is what fitting the regression line. In that one totally only 40 data items were there here. Now similarly the second question here, if this is linear continuously, what will the total number of now here this is right. What we did here, it is we checked only how to load the path. Now here you need to write a code that the implementation where is this, right? And this is implementation. So model implementation, you need to write this entire data that. So here you are defining the method least squares. This function after that, once that is that code is used to load the data. Next by using this you need to compute that one. And this is about first question. Similarly the second question, Kelly-Bill's law and a linear regression. Here also the similar logic. Minus 1 means still a last number. Minus 1. So minus 1 means we are moving last to the first in Python code, Python programming we. NP dot shape means how many elements were there in the x and how many elements are there in the y. That is what it is explained. Now, what is the second question here? 5.3. cross this. Okay. Hmm. After collecting the data, after collecting and plotting the considerable amount of the data, comparing the body mass versus metabolic rate of a variety of animals, early 20th century, biologist Max Kaliber noted an interesting relationship between the two values denoting XP and YP, the body mass and metabolic rate, kilojoule per day, of a given animal respectively. Treating that body mass input feature, Kaliber noted that visual inspection that natural log of these two values were linearly related. That is W0 equal to log XP plus W, which is equal to log P. Then log XP comma log YP equal to P equal to 1 to 2. Each representing an animal reading the some small back chinned hummingbird in the bottom left corner to a large walrus in the top right corner fit a linear model. Again fit a linear model in shown in figure 1.9. This 1.8, this 1.9. 1.8 to 1.9. So we are fitting this one. So that's the reason you please go through the first unit also very clearly. Each representing animal ranging from the small black to small black chinned hummingbird to the bottom left corner and bottom left corner, and this is at here, and at the right walrus, top right corner it is walrus. That is, now for this one we were asked to fit a linear model shown the data set. So 1.9, the data set is many natural sciences. Where is the data set here? Let us figure similar to the Calvert fold slope registration. This relationship compared to small bird species, the metallic figure associated the example to large mass walrus transforming that various animals. See the text for further details. Okay. In maybe here it is given. Okay. The data set name it is given. Kilbert's law data sets. Yeah, this is Kilbert's law data. So all the data sets also freely available in that one. Even in this one also. Only X and Y. Only X and Y. If I see here anything else, Kilbert's only one I have. Kilbert's is only one I have. X value and Y value. The same structure here. 1498 are the number of data items. Similarly, third one, method least square cost for a single Newton step. Single Newton step is nothing but gradient only. So the question here it is third one, 5.3. Okay, still here. Use the optimal parameters if optimal parameters found in part A along with the properties of the log function. The function it is given here log, otherwise this one if I write here log e power w naught, log e power w naught. Okay, how it is connected to the linear, let me explain you this. It is given in terms of the log. Where are you? Yeah. Let me connect to my DC pen. This one I can write here. As per the properties of logarithm, we know that this one I can write here log e power w0 plus log xp w1 is equivalent to log yp. Actually here this entire, if I choose this as a y star, this is a plus b star x, I can write here b star uh, x star b. I can write like this. I can write like this. So to the existing y values, logarithm of that one I need to choose, this one logarithm of this. So finally I need to compute w0 w1 w0 w1. So the normal equation should be sigma w0, yeah, okay. The normal equations I can write here are to avoid confusion, y equals to b times x to x star plus a. I can write like this. So in that one unknowns are a and b, because y star and x star were given to you already in that. Then to compute b here, the coefficient of b is 1, the coefficient of b is x star, coefficient of a is 1. Then normal equations will be sigma y star equals to b times sigma x star plus a times n, and now coefficient of this one will be sigma x star y star equals to b times sigma, this is x star square plus a times sigma x star square. So by using this I can compute clearly both a and b. In place of a there is a w0, in place of b there is w1. By using this we can compute that. Similarly, if you go through this, you can compute the rest. So for all the problems, data sets were given very clearly, and you are asked to compute the model. Model can be computed by using the Python implementation. Now use your fitted line to determine how many calories of an animal weighing 10 kg required. Suppose here is the relation. Believe that the relation is log y star is equal to, believe that the relation is w0 equal to, for example, 40.3 plus log xp, w1 is 27.9, for example, equal to log yp. Now this input is given to you already. What is the input here? Log 10, weighing 10 kg. So then plugging this 10 kg here, 40.3 plus log 10 by 27.9 equals to log yp. So like this you may compute that. Similarly here, sixth one, what is the question here? Third one is also the least cost function and a single Newton step, the same. Here x1 x2 two inputs were given, one output will be given, one output were given. So in this case here what I can write is in this case here y equals to a plus bx1 plus cx2, this would be that. Then the normal equations are here. For me a b c are unknowns. Coefficient of a is 1, quotient of B is x1, quotient of C is x2. Simple logic. Multiply with the coefficient of unknown and apply summation. So we'll get here sigma y equals to an plus b sigma x1 plus c sigma x2. This is the first normal equation. Coming to the second, multiply with x1 and apply summation. So sigma x1y equals to a sigma x1 plus b sigma x1 square plus c sigma x2 square. This is the second. Third one, multiply with x2, sigma x2y equals to a sigma x2 plus b sigma x2 x1 plus c sigma x, sorry, this is x1 x2, this is x1 x2. Now x2 square, this is the third. By using these three you can compute that. By using these three you can compute that. In the computation, x1 value, y1 value, sorry, x1 value, x2 value, y value, these were the given. I required sigma y means find the sum of these. Sigma n means how many are there, count that is size in programming language. Sigma x1 means add this one, sigma x2 means add this, sigma x1 y, x1 y, it is not there, so x1 y, whichever is missing, just develop that and find the summation. Sigma x1 it is available, x1 square it is not available, so x1 square, and simplify. X1 x2 it is not available, so x1 x2, and find its summation. X2y it is not there, so x2y, and sigma x2 it is available, x1 x2 or x2 x1 both are same, x2 square. By computing and substitution, that you may compute a value, b value, c value. That is what it is asked here. So a single Newton step can minimize the least square cost linear regression using single Newton step perfectly normalize the least squares over the data set. And this here the data set is also given. Data set roughly lies on hyperplane. That fit provided by the perfectly minimized least square cost should be very well fit a cost function, history plot, and take to check whether to check that you have turned parameters your linearity model. So like this we may compute numerically. Now programming aspect is also quite similar. It is given in the execution. Similarly, solving the normal equations. Solving the normal equations, we already explained this. And Lipschitz constant for the least square cost. Compute Lipschitz constant. So appendix A6.4. If you open that, you may get the data set. How to compute that? Compare the least square cost and least absolute deviation cost. Repeat the experiment in the example 5.4. You will, so whatever that you are doing here, whatever that you are doing here, on this you need to compare these two, least squares and least absolute deviations, and empirically confirm the convexity of a toy dataset. Toy dataset is also there. Confirm the convexity. 5.7, what it is given, let us see. For a convexity, convex means what I can say that it is in this form. In case of the complex data set, the data set might be like this. For a convex data set, it guarantees the minimum. It guarantees the minimum. And here 5.9. Okay, 5.8. What is the 5.8 here? Where is this? Okay. The least absolute deviation cost is convex. Proof. Okay. Here W1, 2 points W1, W2, in between the relation it is given here. The least absolute deviation cost is convex, and prove that least absolute 5.8. It is simply the derivation of that one, 5.8. That's it is not given. 5.9. housing price and automobile miles per gallon prediction. So two data sets here, example 5.5 and 5.6, Boston housing and automobile miles per gallon data set. Because the large variations in the input values, these data sets you should standard normalize the input features to each of the detail section. About this you may study in the 9.3 prior to the optimization. Improper tuning and the weight regression. So improper tuning weight regression 5.10. Improper tuning of the weight regression. So what happened here, it is weighted regression means if a particular condition is repeated multiple number of times, later we executed that one in the form of this. So weighted regression depend upon the requirement, we may update this beta 1, beta 2 and so on, beta p. This is so multi-output regression, example 5.9 you can see the implementation, and example 5.9, 5.3. Yeah, example 5.9 you can see that one. So for this one, multi-output regression using the total data set with the input dimensions 2 and output dimension c equal to 2, input to 2 and output 2, where we have plotted input 1 or one input, and we have plotted one output. We have plotted the input and one output value in each two panels of this. We tune the parameters an appropriate linear model by minimizing the least squares here. Here about only one output it is. Now we required two outputs here. For the two outputs, this is by using this w value is here n equals to n and c equal to 1 means only 1, so c equal to 2. In the last session we explained that. Okay, here n equal to 2, c equal to n equal to n equal to c equal to 2. This. By using this model we can update the things here. It's a implementation, Python implementation also explained clearly in this. And where is this? Right. About the end nodes here, least square cost function is always a convex. About this, it is a convex means it look like a squared function. How it look like a squared function, it is explained here. You try to develop this one. If you are not in the position to develop this, I may explain in the classroom this one. So with this first part completed, second part I may explain and I may share the same.